everyone, thank you very much. Today I want to talk about design automation and simulation. And design automation actually paved the way from the first really big computer to now what everyone here has in their pocket, their tiny smartphones that are way more efficient because they include way more complexity. And we as a group think that we can use the same methods for microphysiological systems and help design them, and that's what I'm going to talk about today. So let's first talk about how design automation works for circuits and systems. Since I'm in a room full of MPS experts, I just want to start from this side. So we go from a specification to a realized design. So what you can see right here on the side, that's the chip design, and sometimes on the PCB you already see the electrodes that look like microfluidic systems almost. And how to get from now a constraint or a specification to this end design is by using several abstraction levels. So by using all of these abstraction levels, you can go from, it facilitates how to translate these specifications into something else. And then, of course, we need to check for correctness, because in each of these systems you can lose information, which would be a big problem. And, of course, we need a support in the debugging of errors that can come along the way. Now, let's talk about how we can utilize this for microfluidics. Again, we have a specification, and that leads to a design for a lab on chip, and eventually, of course, also an MPS. And then you fabricate your lab on chip or your microphysiological chip design, and you get a fabricated lab on chip. However, if that doesn't work, so some of the fluids don't flow, it doesn't work as intended, you have to go back and debug your design. So change some of the design parameters. If you now have an idea, change something, fabricate it again, and then you end up in some sort of a loop where you have to fabricate each device and each idea rather than using a validation method like a simulation, where you use CFD simulations or, of course, other simulation methods that can validate your ideas before going into practice and fabricating. Now, the design itself as well, here is where we can use a lot of more effective ways to go from the specification to your eventual design, because it's quite manual and time-consuming, especially since the people developing novel microfluidics systems, they're not necessarily microfluidic experts, but they're end users wanting to implement something on a microfluidic platform. Now, this is where methods for design automation come into place. So we want to use all of the knowledge we already gained in the electric engineering community and apply it to microfluidics and MPS systems. So what our group has been doing so far is, first of all, these are quite niche topics, but the first small thing is a meander designer, that it just creates a meander with a specific resistance. And this is important because, of course, the longer the channel, the higher the pressure difference between start and end. So this way you can already model where a fluid will flow and at what rate based on your design. And this is now in a more complex system in a gradient generator. So you now have multiple layers of these meanders, and then you can specify at the outlet specific fluid concentrations, and therefore you don't have to necessarily design the chip. You just say, okay, I want this concentration, and it automatically generates a design that would work for this. And this was validated again using simulations and then also physical realizations. And lastly, and of course, place and route algorithms are very much used in the electrical community, but we can also use it for placing modules, and these could just be black boxes, or they can be specific module for your design. And then it automatically creates channels that have a defined length, and they can move around obstacles, so not cross them, they don't cross each other, and you define the flow rate or the pressure difference in these meanders. Now, as validation, I already mentioned that we want to use simulation, so we can use different abstraction levels, and one of them is, of course, computational fluid dynamics. I've seen at this conference a couple of people using already simulations that are very accurate, but in very complex systems, they can get computationally very expensive. You need high computing power, you need a lot of time sometimes until the simulation is finished. As an alternative, you can use a 1D simulation, and this is especially works well for microfluidic systems, since here we always have a laminar flow. Therefore, we can translate the equations, the Hagen-Poiseuille equations describing this flow, to Kirchhoff laws, and now we have an abstraction to the 1D level that's very, very efficient. However, it is also quite abstract. So you have a trade-off between the accuracy and the efficiency, while sometimes it will always make sense to go one or the other way. That just depends on the design you want to simulate. Now, we're also combining both of these methods. So you have a 1D simulation for most of your network, and then in regions where you want a more specific and more detailed validation, you use a CFD simulation for these regions. So for example, here, if there is like a node that connects 4 channels, this is something you might want to look at using a CFD simulation. And we're trying to develop all of these tools open source and usable for anyone, and they're on our website. But now I want to get into why all of us are hopefully here, which is how can we use design automation for microphysiological systems. And we change the specification or add on to the specification for microfluidic systems and change it to a physiologically based specification, as well as lab constraints you might have in the lab. Again, the design will then be based on a method for design automation, and then you use simulation to validate before fabricating your MPS. But at the end of it, you have a final design that is validated that can then go into a fabrication process. Now, let's look at this in a bit more detail. So we want a specification, and this is just a schematic of a microphysiological system. And we want to now model the circulatory network, since this is the microfluidic circuit that has the most similarity to our electrical engineering basis. And we want to connect multiple organs. And in that, we also want to implement a compartmentalized MPS, because we've seen in a lot of literature that that's what's being used. And also it has this separation of concerns between the organ modules itself, then we have the membrane, and then we have the circulating fluid network. And the final goal is to model the tissue culture and the interaction of the organs in a physiologically relevant way. Looking at a schematic, again, it's the same schematic, I've just separated this, and this is also good for people coming from both sides to maybe abstract a bit the idea of an MPS. So we have multiple layers, and this doesn't necessarily mean that this is the way it's fabricated. At the top, we have an organ module layer that contains our organ modules. These are separated by membranes from our circulatory network, so we could connect all of the organs that we apply for now a syringe pump, but any pumping system could, like in theory, be applied. And we also have a recirculation pump for the circulation of the media. And then the constraints are that we want to have the tissue scaled to each other, so the volume of the tissue should be scaled, and we're doing this in a linear fashion. There's of course other scaling mechanisms, but we found that we had good values in literature for this. And we defined 2 different types of tissues to verify the geometry of the tissues. So this doesn't necessarily mean that these are the only tissues that could be applied with such a method. It just means we wanted to have 2 different geometries to implement in this automated method. So we have a layered tissue and a round tissue. And then we want to look at the shear stress. so the shear stress that acts on the bottom of the membrane in our network, and we define it at each membrane. So each membrane has a specified shear stress acting on it, and that is of course based on the flow rate flowing underneath that module. And lastly, we also wanted to include physiological perfusion, so the crosstalk between the modules somewhat resembles the blood flow in a human. And this is also something where you could include dilution in your system, since often the volumes in MPS are much higher than the blood volume or the fluid volume in a human would be. Now, again, how are we going to utilize now design automation? We want to relate the microfluidics with an electrical circuit. So now looking at our microfluidic network, or part of a microfluidic network, we have a relation to an electric circuit. So each resistance in a channel now corresponds to an electric resistance in the electric circuit, and therefore you can sort of map out and eventually simulate the whole system. The general idea for now this schematic I just showed was we want to compute the flow rates in the entire channel network, and this is, as I mentioned, based on the Kirchhoff's laws. And we define the module flow rates, so the flow rate underneath each of the modules, as well as the perfusion flow rates. So these are the flow rates we already know, they are set, and now all of the other flow rates we can compute based on these flow rates. So we use supply and discharge channels to include more fresh medium, replenish the medium, and then eventually this would also lead to a stationary fluid volume in our chip, or it's not a stationary system itself, but you don't lose or gain any volume in the system. And then they are supplied by feed and drain channels respectively, and eventually this allows us to now have a flow rate that you need to apply at your pumps. Now the geometry definition is based on the flow rates we just calculated, and again we need to do a pressure correction. So each of these loops, the gradients of the pressure need to be equal to 0 if you take into regard the direction of them. And based on this, we could then compute all of the necessary channel resistances and also all of the channel lengths we need. Again, thinking back to the meanders, we insert meanders to now have specific lengths for each of these channels, and therefore we have the required flow rates by these, defined by the geometry itself. We correct the offset in case there's a collision of our feed or drain, and thereby we repeat this until we find a solution. So at the end, we find the smallest possible network that includes all of our flow rates in the way we want them, and that should work as we want. And this is basically the whole idea of the method, but let's look at an example to make it a bit clearer. So we just defined 3 tissue compartments, and these are scaled based on tissue constraints, but all of the data we got from literature. So we just placed them in a sequential mode, and again, they were automatically scaled. And now the method itself gives us, as a result, an automated microfluidic network. So we have the meanders, we have the connection between our modules, we have our inflow and our outflow. And again, this is maybe important to note, this is a recirculation pump. And if you have more constraints for this pump, you of course can also input them. Right now, it's just a definition for this channel that we used. And we evaluated this using CFD because the method itself is already somewhat based on the 1D simulation, and that's why it made sense to, in this case, use a different simulation method to have a separation of concerns almost. And our deviations from the desired values were typically very, very low. So you got the desired perfusion rates, the shear rates, and the flow rates in your entire network. And we, of course, tried this out with different modules, different combinations, different numbers of modules. And they all worked very, very well. And in conclusion, we hope that this is like the first inclination or going towards design automation and simulation methods for the microphysiological community. So we take the specification, we have a schematic MPS design that leads us to all of the flow rates in our model based on the constraints we previously put in. We validate this using simulation, and eventually it could either already lead to a fabricated design, or it could lead to an idea or finished design that you can then fabricate, since the fabrication is, of course, a process in itself. With that, I'd like to thank everyone for listening and give a special shout out to my colleagues, Philipp Ebner, Michael Tacken, and my supervisor, Professor Robert Wille at the Technical University of Munich.